Okay, so to conduct the Leibniz homogeneity test for variance, you just have to go to analyze. Have you clicked on that? Then you go to compare means. Go to compare means. Then go to one-way ANOVA. I will see it down there. Analyze, compare means, and what? One-way ANOVA. Now select all the indicators and put them in the list called dependence. Select all, right? But remember, in our case, the numbers, they are more than 100. Are you aware of that? They were 119. Okay. We'll take some few. Okay. So we can take some few, right? So we can do away with, let's do away with the demographics.
Just take the rest.
And take the rest. And then we also
exclude the questions that we added.
Is it?
We add the questions that we took off. He said, so we
this is a different data. Let me open the one that we have. This is the data I use for the man's work.
Where the one you gave us.
Okay, so we get the data file.
But we transform some data.
Yes, so that one we will not select them. Those that we have transformed, we will not select them.
Okay. I will not. Is it the transformed one or the one?
The transformed one.
That will be the last two options.
So,
Did you say it yesterday when it transformed?
Yeah.
so you go to analyze, and then you go to compare means, and then go to one-way what? ANOVA. You right click to display variable names as usual.
Compare means. One-way ANOVA.
And you select, okay, select up to OP, okay? OP 14. Hello? Are you hearing me?
yes.
I said you select up to what?
OP.
14. Okay. Then you go to your contrast. Oh, that one you know.
To the variable list.
Let me see if I have wave here. Oh, I don't have wave. I don't have wave in this data.
And this data, okay. But
I don't have wave in this data. So it will be difficult for us to calculate for it. By the way, let me open another data that has the wave. So you don't have that particular data. Okay. So take note of the wave, okay? Let me open this data file.
So meaning say in this data you didn't do it.
Yeah, I didn't create the wave.
Okay.
I didn't create the wave. Let's come to this particular data. This data, I have the wave. Have you seen? That's the first one there. Have you seen it?
Yeah.
Yeah. Okay. So I'm selecting the items. But this one, the items are many, so I'll not select all. So go to analyze, compare means, and then one-way ANOVA. The same procedure. So we select the items, which is not supposed to be more than 100, okay? Then we put them in. Then we go to options. Then you click on homogeneity of what? Variance tests. And then continue. Then which factor are we comparing them on? Is what? The wave. So the wave should not be part of here. It should rather be selected and placed here. You just click on that. Yes. You select the wave and put it at where the factor is. Then click OK. That's all. So it will give you results like this. And you calculate based on mean, based on median, based on mode. So you have to look at the level of measurement. You have to first of all look at the level of measurement of that particular variable before you interpret your results.
Okay.
So work status, what level do you measure work status? Is either you are a manager, you are a farm manager, or you are the farm owner. So at what level are you measuring it?
Nominal.
Nominal. So what is the central tendency for nominal?
Maybe we take mode.
So you can take what mode or what? Median. There's no mode here. So we look at this one. This is the median. That is what I want you to understand. And you look at the sig value. Is it less than 0.05?
That is it. I get that. I will see what
0.949. It's greater than 0.05, right? So they were willing to what? To answer. That is what we see. Gender is at the nominal level, so you can also base on the median. So the answer. Is that not it? Now let's go to some of the killed items here. So this one we use mean because they are measured at the interval level. So look at the mean and then look at what? The significance level. So were they willing to answer?
They were willing.
Good. So if you look at it, they are almost all of them are what? Significant, are not significant. Which tells us that we have no threat of non-responses. In other words, the people were happy to respond to our questionnaire. And that is what we call no-response bias.
Non-response bias.
Okay. We want to test for normality of your data, and in most of the differential statistics, particularly for parametric tests, part of the assumption is that you are required to test the normality of the distribution of the data. So when we say your data is normally distributed, it means that in a simple term, somebody will say that the mean, standard deviation mode, or the central tendencies must all converge around the same point. Okay. So that will say that your data is normally distributed. But the reality is that it is very difficult for you to get a perfectly distributed data. So the data could be what? Skewed. So we have two instances. When we talk about ketosis and skewness, when we talk about ketosis measures the wickedness of the central point as we speak. Then ketosis talks about, skewness talks about the divergence from the middle point, either at the left or what? Good. So these are two extremes that we can use to gauge our data if it is normally distributed or not. Because I said that it's very difficult for you to achieve a perfect measure of it. Now if you want to test for the normality of data, we have at least three approaches. Okay, you can use the mean, you can use the ketosis and that of what? Standard deviation to check. You can also use the Kolmogorov, Swinoff, or what? The Shapiro-Wilks test. Or you can also examine the distribution of the QQ plot or the histogram to check if the histogram is forming a bell shape, or if it is a QQ plot. Most of the data points should be found on the line of best fit as we just saw. So most of the instances they will tell you that your dependent variable should be normally distributed. So let's use this situation, our data, our original data that we used, to check for normality of some of the variables. Okay, so maybe we will want to check for the normality of the variables forming operational performance. So as illustration, we will use OP1 as our dependent variable. Okay, because the assumption is that your dependent variable should be normally what? Distributed. So to test that, you just go to analyze, you go to descriptives, go to analyze descriptives, then go to explore. So in exploring, we have to right click to display variable name and then go and select OP1 OP1 and put it at the dependent box. So OP1, put it at the dependent box. Okay, then you click on statistics. I think everything is checked in, it's okay. Click on plots, click on histogram, and deselect item and stem and leaf. Deselect it, okay? Then you come and select normality.
The statistics should select on descriptive.
No, it is already selected, so don't continue. Then you come to plots. At plots, you select histogram and normality plots with what? Tests. Click on continue and go to OK. But make sure that at this display session, it is taking both statistics and what? Plot. You can vary it, and if you are interested in only the statistics, you select it, okay? Or if you are interested in the plots, you also what? Select it. So here we are interested in both the plots and statistics, so that's why we put it there and click on OK.
And the factor list, don't leave anything.
No, don't worry yourself with it at all. Okay, so this is our output. This is our output. Now let's examine this. The descriptives. The dependent variable is quick response to changes in demand. Is that not it? That is what we call the OP1. It is the quick response to demand. Let me put it on a word file. Okay, so this is the OP1 that we were talking about. We want to check if it is normally distributed or not. If you are using these statistics, we say that the ketosis and then the skewness should be close to what? Should be close to what? 0.
Yeah, 0.
So are they close to 0?
Depending on
Are they close to 0? 1.66, is it close to 0?
no, no close.
Okay. 2.57. Okay. So you should tell us that our data perhaps is not possibly normally what? Distributed. But we also have the other one where you have to divide the statistics, right? Statistics divided by the standard what? Error.
1.6.
So do it for us. For ketosis or skewness, what did you get? Skewness is 1.689 divided by 0.155. What did we get? Divided by
0.1.
the book shows it there. What did we get?
I'm getting 10. 10.889.
10 point what?
9.
But we said that it should fall within the z-score of negative 1.96 and what?
Positive 1.96.
And positive
1.96.
1.96. 1.96. It's because our p-value is pegged at 5%. Okay? And our confidence interval is also pegged at what? 95%. That's why it is the z-score that we rate that we want is supposed to be within the 1.96, negative and then positive 1.96. So if you look at this, since it doesn't fall within this range, we conclude that it is not approximately normally what? Distributed. Okay, that's all. We also have other ways to also evaluate it. The next one is that we use the Kolmogorov, Smirnov, or the Shapiro weight test. So that one, it says that the significant value measured by the p value should be what? Should not be significant, and therefore it should be more than 0.05. For Kolmogorov, if the sample size is less than what? 50, then you use it. For Shapiro, if it's more than 50, then you use it. Here our sample size is what? 248. So we use the Shapiro.
Shapiro is about 50.
Yeah, it should be about 50.
So that is nice. It is significant.
So is it normally distributed? Okay, so since it is significant, the p-values are less than 0.054. We see that the data is not approximately normally what? Distributed. Then we go to the last bit of it. We can use the QQ plots, or you can use the histogram to also check on that. Okay? What happened? If you draw a point to the other thing, you see that it is not taking a payload shape. Is that not it? Do we have the one that we can use to draw? Okay, so if you draw a line through the central midpoint like this, you will see that it is not taking what? A bell shape, right? So we can conclude that it is not approximately normally what? Distributed. That's all. Okay. Then we can go on to examine this the normal QQ plot, right?
Yeah.
When we examine it carefully, we see that the points
Only 2 hours. Another 2 hours.
only two. Look at this one. They quite far away, right? Only two are almost on the line of best fit. So in that situation, we conclude that the data is not approximately normally what? Distributed. Is that okay? So at least we have seen about 3 means that we can use to check if your data is normally distributed or not. Thank you.